Let's take a look at this problem. Strontium-90 decays with the emission of a 2.8 mega-electron-volt beta particle. Strontium is chemically similar to calcium and is taken up by bone. A 75-kilogram person is exposed to waste from a nuclear accident, absorbs strontium-90 with an activity of 370,000 becquerels. Assume that all of this strontium-90 ends up in the skeleton. The skeleton forms 17% of the person's body mass. If 50% of the decay energy is absorbed by the skeleton, what dose equivalent in sieverts will be received by the person's skeleton in the first month? Well, this looks complicated. There's lots of data here. But ultimately, it's a question of dose or dose equivalent. Now, remember, the dose is from a beta particle. And for a beta particle, the dose and the dose equivalent are the same because the RBE, the relative biological effectiveness of a beta particle, is just 1. So when we compute the dose in grays, we'll have the same number for the dose equivalent in sieverts. And a dose in grays, dose in grays is the joules per kilogram that are absorbed. So we need to work out two things. First off, we have to work out the energy that's absorbed, and then 2, we have to work out the mass of the tissue that absorbs that dose. Now, the mass is pretty straightforward. The person has a mass of 75 kilograms. Of this, 0.17 is the mass of the skeleton, and so you end up with a skeleton mass of 12.75 kilograms. And we're going to keep a couple of extra significant figures because it's the intermediate stage of the calculation. The energy is just going to be equal to the number of decays times the energy per decay. Okay? That is going to be the energy liberated. Now, the number of decays is just going to be equal to the activity, because the activity is the decays per second, and I'm going to multiply that by the number of seconds in a month, okay? And so if we do that, that's going to be the number of decays in a month. That's the number of decays we have in the first month, and we're going to multiply that by the energy per decay, and we're going to get an energy value. Now, to get the energy per decay, we're given it in mega electron volts, but we don't want it in electron volts. We want it in joules because the dose is looking for joules per kilogram. So we'll convert 2.8 mega electron volts is equal to 4.5 times 10 to minus 13th joules. So let's work out the energy now. We have 370,000 decays per second, okay? Over the time of 1 month, and 1 month is 2.6 times 10 to the 6th seconds. That's the amount of time in 1 month. That's how many decays we have per month. And we'll multiply that by the energy per decay, which is 4.5 times 10 to the minus 13th joules. When we do that calculation, the total energy liberated in these decays is 0.43 joules. So the dose, we'll calculate this way. The dose is 0.43 joules. That's the energy liberated. But we're told that only 50% of the decay is absorbed by the skeleton, so we'll multiply that by 0.5. And then we divide that by the mass of the skeleton, which is 12.75 kilograms. So we end up with 17 milligrays. That's our figure. But of course, we weren't looking for the dose. We were looking for the dose equivalent in sieverts. But remember, RBE for the beta particle is 1, so the dose equivalent in sieverts is the same as the dose in grays, and so the dose equivalent, 17 millisieverts. Now remember, it's about 3 millisieverts per year as a typical dose that a person gets from natural sources. So 17 millisieverts is a significant dose. That's 6 times the yearly dose concentrated in the skeleton. So this is kind of a big deal, but we expect that to be true. This was a person who was exposed to waste from a nuclear accident. So we're anticipating this is going to be a difficult situation. And in fact, that's about what we find. So our answer seems reasonable.